All right. So the whole unit is electricity and magnetism. And you might wonder, are those two things related? Uh, yes, but not in the way you might think. So you'll have to stay tuned for that one. And you guys have probably experienced this, where you've probably not seen the spark, but there's actually a spark too. You could visually see it if it were dark enough. You've probably reached out to like some metal object, like a doorknob, and you've gotten a shock. And usually it involves something you were doing with your feet. You were probably rubbing your feet on something, a particular kind of carpet or rug or something like that, or some other way, and you picked up a charge. And that is a discharge of that charge. In other words, the charge jumped. So notice it jumps. It can jump. It can build up and it can jump. It also, you've probably experienced this on a real dry, low humidity day. You've probably had like clothes clinging to you, which is uncomfortable. And it can happen. It doesn't just happen to women, it happens to men too. And other things. I'm not a cat. Or you've taken stuff out of the dryer and you've heard crackling. You've felt crackling. You might even feel it on your arm hairs might start standing up. If you did this in the dark, which is difficult because a lot of dryers have built-in lights when you open the door, but if not all of them, so if you do this in the dark, you would actually see sparks too, besides just hearing them. And of course, you've all had the experience of trying to comb your hair on a dry, non-humid day, and the hair wants to stick to the comb, and it's almost impossible to comb your hair. And you've probably had the pesky little brother or cousin or something that rubs their feet on the carpet just on purpose so they can come up and zap you. This is also the same effect. Much greater, of course, much greater. But notice one thing, it's jumping. It jumps from cloud to ground or ground to cloud. And it's still jumping. The key point is that it's not flowing. It's not a flow, it's a jump. With whether you're touching the doorknob, it's a jump. Okay, so what can we say about electrostatics? Well, first let's just talk about charge. Remember, I told you last time that it's very hard to define this. It's one of those very basic definitions that at the very bottom of everything. So it's a characteristic of a particle. The charge can be negative or positive. It's a characteristic of a particle. That's about all we can say about it. And that it's positive and negative. That's it. I really can't say much more than that. I know it's very unsatisfying, but there we have it. What's the source of the charge? What's the source of this thing? Well, we do know the source is, we go back to the atom, where we have this isn't a great representation of the atom. It's really hard to represent the atom in its true form, but you have an electron cloud model of a carbon atom where you have a small dense nucleus surrounded by electron cloud. Okay, and that's the source of the charge, those electrons and protons. As you remember, electrons have a negative charge and protons have a positive charge. So the proton is a large particle in the nucleus of an atom. The proton has a positive charge. Okay, and you guys hopefully remember that from chemistry, and hopefully if not, this will refresh your memory. So Okay, and then an electron, that's the source of the positive charge. And the electron, the tiny particle, which is in the outer region of the atom, referred to as the electron cloud, the electron has a negative charge. Okay, that's our origin statement. That's where they're coming from. The protons and the electrons in the atom are the sources of electric charge. Now, this guy who you guys I know are walking around with a bunch of pictures of him in your wallets, Benjamin Franklin, he was an American statesman. He was never president, of course, and he was also considered a great scientist. You might not know that about him. He's the one responsible for naming the charges. He did a bunch of early work on electrostatics by rubbing different materials together and seeing what would happen. And he noticed that there were two types of charges, and he named them. And again, he could have named them black and white. He could have named them up and down, north and south, but he decided to name them positive and negative. Now, and why did he name one negative and one positive? Was there something wrong with one of them and something good about the other? No, it was just random. It's almost a flip of a coin. And it's a bit unfortunate because we're gonna find out it would have been nice if he'd named the negative, if he'd flipped those. It would have been nice, but it didn't happen, so we had to live with it. And you've probably heard about his early experiments with the kite. He would fly a kite during thunderstorms, and he noticed the key that's attached to that. He used a regular string on the kite, but he also had a wire going to the kite, and then the kite went to the key, and then the wire from the key went down to that little jar down at the bottom on the ground by the boy's leg. That's called the Leyden jar. It's named after a city in Holland, Leyden, Leyden, and it could store charge. And we'll find out how it did that a little bit. And it's a precursor to an important electronic component that you guys are using right now. And he was able to store the charge. Now, so this electrostatic charge, the things about it are that it can be stored and it can jump from one place to another, but it can't flow. It doesn't flow. So that's what makes it different. We're going to have our next subunit is going to be electric current. That's electric charge that flows. Electrostatics is charge that doesn't flow, but it can jump, and it can be stored. So you can store it, it'll jump from one place to another, but it won't flow. That's what makes it different from electric current. He noticed that what he named positive, whatever he rubbed wood or glass, whenever he rubbed those with silk, they would take on a certain charge. And he could tell because he'd have other stuff that when he rubbed plastic or hard rubber with fur, it would take on another charge, and he decided to call that one negative. He noticed these were different charges because they'd repel each other. The object so charged, if he had like a piece of wood or a piece of plastic, a piece of wood rubbed with silk or a piece of plastic rubbed with fur, he noticed those objects would repel each other. And so he said, well, it looks like there's two different kinds of charges. No matter how many different combinations of things, it was always the same ones. It was always the same ones. So he decided, okay, that one's going to be positive and that one's going to be negative. And this led to it was an early discoveries of static electricity, and so it deals with charges that do not flow. They can jump, but they cannot flow. They can be stored, but they cannot flow. So that's the important parts of this. The other thing that you discovered, hopefully, is that opposites attract each other, and that likes repel each other. And that winds up being the basic law of electrostatics. Objects that are similarly charged repel each other. Objects that are oppositely charged attract each other. All right, so yes, we do have a video with sound. So let me start that.
Do you know what this is? Aside from the obvious, no idea. It's amber. Petrified tree sap. The Greeks used it for electrostatic experiments.
How?
Well, here's a piece of fur. What happens if you rub the amber with this fur? The fur tries to stay near the amber. What effect does the rubbed amber have on this paper?
It attracts it.
And the fur? It attracts the paper, too.
This is just static electricity, isn't it?
Right. Do you know why we call it electricity? Not really. Why? Because electricity comes from the Greek word for amber. No kidding. The Greeks explained how rubbing the amber with the fur would make both the amber and the fur attract the paper. They imagined that both the amber and the fur were full of a fluid. As the fur moved against the amber, some of the fluid from each of the objects was forced to move. So, a surplus of one fluid or the other was thought to cause electrostatic attraction. Benjamin Franklin was a famous scientist and inventor. He began life as a printer, but at the age of 40, he saw some experiments in electricity and was so fascinated that he sold his printing press and spent all his time experimenting. In particular, he wondered if simple electrostatic effects could explain lightning. In 1752, Franklin decided to test his ideas about lightning in his famous kite experiment. He hoped that he could attract the lightning to the pointed wire at the top of the kite, down the string, and through the key to the ground.
That sounds just a little risky.
Yeah, do not try this at home.
Exactly. In fact, several experimenters weren't as lucky as Franklin, and they were killed by the lightning.
But nothing happened to Franklin.
No, he survived, which is lucky for us, because he advanced our understanding of electrostatics. In his work with electricity, especially lightning, he theorized that all matter contained a positive fluid.
So then something with a positive charge would have more of the fluid.
And that means that a negative charge happens when something has too little of the fluid.
That's right. Franklin's explanation of electricity is easily illustrated by lightning. He said that since lightning comes from an excess of positive electric fluid and seems to move from the clouds to the earth, charge moves from positive to negative.
What did Franklin do with all this positive electrical fluid that he got from the lightning strikes?
Fortunately for him, in 1746, Peter van Musschenberg reported on an accidental and nearly fatal discovery. He was trying to capture electricity in a bottle filled with water. It was connected to a machine that produces excess electric charges using friction.
What happened?
An assistant accidentally touched the wire connecting the machine to the bottle. He received a tremendous shock. It was then that van Musschenberg realized that he had devised a method of storing electrostatic charge, a Leyden jar.
Okay. More on Leyden jars later. So we got three methods of charging, and the first one is by friction, rubbing electrons off an object. Let me show you that one. right, I've got, actually you guys would have been doing this in class last time, so unfortunately we don't get to do that. Yeah, that's good. All right, so what I've got is, this is a PVC rod, like the same material as you make sprinkler pipes. Probably it's polyvinyl, PVC is polyvinyl chloride. It's the material that this is made of. It's just a hollow pipe. And I've got a piece of fur. So if I take the, you see, if I put this near the what's called a pith ball. This is a pith ball. It's the pith is the center of, like, if you took a tree and cut it down and had the center of that wood is pith, and so that's a pith ball. It's the same kind of material. And if I rub it this, then I bring it. You can see it starts attract. It's now attracting that pith ball. So again, once again, the demonstration that this is stronger than gravity. And I'll let it touch, and I'm not getting it to do the other thing I wanted it to do. Hold on. Okay, so now that's charged because it touched, or maybe it's not charged is the problem. But I've got, I also have glass with silk. No, it didn't charge. What I was hoping would happen would be the other type of charging. And that is really difficult to get it to do it. I don't know why. I have a video of it later where it'll work, but it's real difficult to get that to do it. But you see, this was charged by friction. Same as when I rub the balloons with my hair. All right, let's go back to the PowerPoint. So friction is one way to do it. And technically what you're doing is you're rubbing this. Let me jump to the chase here. No, yeah, I think that's the right way to phrase that. This is all about electrons. And we can talk about protons, but moving protons is real difficult. Moving protons is like trying to move an aircraft carrier. Yeah, you can do it, but it's not as easy as, let's say, moving a jet ski. Moving a jet ski is much easier. Electrons much smaller than an aircraft. It certainly is much smaller than an aircraft carrier, but it's much smaller than a proton. It's 1/500th of the size of a proton. And yeah, you can do this with protons, but they're really stubborn. They're very heavy, and they're not going to move. Okay, so the electrons are much easier to move. The protons, you'd have to have them in liquid where they'd be easy to move. They're responsible for a lot of your brain chemistry because they are in liquid and they are moving around in liquid. But for our purposes, for this electrostatics, and when we get to current electricity, what we're talking about moving are electrons. Okay, so that's just something to prepare you for. All right, the next method of moving is electrostatic induction, and this one is difficult to grasp as a concept, so I'm going to try, and this will be one attempt, and we'll make another attempt. It's also bad that we have a word here that's used, induction, which will be used later, because there's another type of induction that's even more important than this one, and that's electromagnetic induction. So the adjective is vital here. There's a difference between electrostatic induction and electromagnetic induction. They're not even really similar except for the fact that electrons are involved. So here's my first attempt at explaining this one to you. Electrostatic induction. Start with figure A. Start with figure A. So we have, like, let's say the pith ball I just had. It started out neutral. It had equal numbers of positive and negative charges. And you saw this also with the sweater yesterday. You started off with a neutral sweater. It had equal numbers of positive and negative charges. And you have something charged. That rubber rod over here on the rubber rod on the left is charged. It's been rubbed, let's say, by friction, and so it's been charged negatively. And you bring it close to the neutral object, and what happened is the charges separate. The negatives are going to rush over. The negatives are going to rush to this side. Why didn't I get a pen? The negative, I still don't get a pen. Why didn't I get a pen? Well, now it's a cursor. Hold on. Why won't the pen draw? So, there we go. Okay, so the positives rush over to this side because they want to go near. Remember, opposites attract, so the positives are going to go near the rod, towards the rod, because it's attracting them. The negatives are repelled, so they're going to the opposite side. Okay, and in B, if I put a wire, this is called a ground wire. Oops, that's an R. It's going to ground. You actually put it in the ground. The negatives, oh, they want to get rid of that. They want to get as far away. They'll take it out. They'll go that way. By the way, notice I'm not touching. At any point I don't touch the sphere. Okay. Finally, in C, now the ground wire is basically, I gave the negative charges a door out, and now I've slammed the door closed, so they can't get back in. So I've lost all my negative charges. Now I can take the rod away, and I wind up in the final one with an object that's positively charged. Okay, so I had a neutrally charged object. This is neutral. The ball is neutral. It has equal numbers. Remember, that's not a charge. It has equal numbers of positives and negatives. It's neutral. Okay, I bring a rod that's charged close to it, but not touching. Can't touch. Okay, the charges in the neutral object separate. The positives will go towards the rod. The negatives go the opposite direction. And if I give the negatives a way out, like this ground wire, they'll take it. They'll leave. Then if I close that avenue so they can't come back in, we don't want them coming back in, I wind up with the situation in C. The negatives have left. All I've got left is positives now in that object that used to be neutral. And then if I take that rod away, that object winds up staying positively charged. Okay, this is electromagnetic induction. Now for your notes, I have a brief summary here. So bringing a charged object near, not touching a neutral object. The neutral object's charges separate, and the charges that are the same as the charged object are given a way out. And so the object will become negatively charged versus the object that you brought close to it. So this is called electromagnetic induction. And no, I never even had a demo on that. Even if you'd been in class, I couldn't have demoed this for you. And the last way to charge something is easy. You touch it. You touch a charged object to an uncharged object. So you wind up charging something by touching it. Not you. You have to be touched by something that has a charge with it on it, and you'll become charged. So most of your experience has been like that you described yesterday, like going down a slide or having someone rubbing feet on a carpet, stuff like that. That's the friction one. You're literally rubbing, and again, we're talking about those light little electrons. You're rubbing electrons off of that object and onto you. You're accumulating electrons, so you're accumulating a negative charge. Why? What about the dryer? What's going on there? You've got materials that are different inside the dryer. You can have like polyester and cotton, right? And they're not the same materials. So as they've been in that dryer running around, rubbing each other, and one is giving off electrons to the other one. One is losing electrons, so the one losing electrons is becoming positively charged. The one gaining electrons is becoming negatively charged. And then when you grab them, you're discharging. And so that's what the crackling comes from. Okay, you're doing conduction then. By touching, you're doing conduction. All right, let's go on. Because of this, we can have, we name two different types of objects, those that want to gain electrons. Those are called conductors. Those are materials that allow electricity to move through them freely and they have because they have loosely held electrons. And these are the metals usually, like copper and gold and iron. So in Franklin's experiment, he's using metal. He's using a metal wire and a metal key. And that Leyden jar, by the way, we're going to find out is coated with tin on the inside and the outside, and has a copper like bulb at the top of it. And why? Why are the metals? Why the metals? Because the metals, when they solidify, they form a crystal matrix, and the crystal matrix kind of holds the atoms all together, and so the electrons kind of get like loosey-goosey about which atom they belong to. So they become real easy to move electrons from one to another. You can bounce them, and you can knock one. It's like not quite like dominoes, but one gets hit, and the next one, it'll hit bump the next one off of its atom, and that one bumps the next one off the next atom, bumps the next one off the next atom, and so forth, and so on. And by the way, for the same reason, these are all great conductors of heat, copper, gold, and iron. Insulators are materials that do not allow the free flow of electrons, and we got rubber and plastic. And you saw me rub that plastic. What was the deal with that? Well, that was different. Remember, these aren't flowing, these are jumping. It becomes charged. They can become charged, but the electrons don't flow through them freely. Okay, we have devices for measuring this called electroscopes, and I have one that I want to show you. Oops, too far, wrong way. Here's an electroscope. What it's got is it's got little glass doors, and the glass doors are so it doesn't, you can see it, but you don't get like the currents, room current of air bothering the two little leaves inside. And these two little leaves, let me do it from the back where I can touch them. These two little leaves are mylar in this case. Traditionally, this was gold leaves, but Mylar works just as well, and Mylar is a lot cheaper. Mylar is like the balloons, the silvery balloons. Those are Mylar balloons. It's a plastic with the metal coating on them. And so what happens is, so I can take my PVC rod and I can charge it by friction, and by conduction, I can add the charge to this thing. And notice what's happening. Since the charge is going to this, by the way, the Leyden jars have a bulb on them like this too for the same purpose, so you can add charge to it. Why are they flying away from each other? Because I've added, I'm pretty sure it's negative charge when you do PVC rubbed with fur. I've got excess by friction. I'm charging. I'm giving it excess negative charges. So electrons are being ripped off the fur. Electrons are being put onto this. I'm touching it, and they're going down into the. They're loading here. They're storing into this device. So you see here, you got examples of charging by friction and charging by conduction. Now, if I touch it, I discharge it, because now it's got excess negative charge. But if I touch it, the excess charge flows into me. Now I've got excess charges, but I'm bigger, so it doesn't. I don't feel anything. So again, if I rub it and then touch it, I'm putting negative charge here, and it's electrons that are moving. The charge has to have a carrier. Charge does not exist by itself. It has to have a carrier of some kind, and the carrier is the electron. So we're basically adding them. I'm rubbing them off the fur, rubbing them off the fur onto the plastic, that by friction, charging by friction, and then I charge by conduction by touching this. And then of course I discharge it. Now I'm discharging, or the charges are coming into me by conduction, by touching. Okay, that's get back to the PowerPoint. Okay, so that's an electroscope. That's one version of electroscope. You have another type, looks like this, called a hollow straw. Same idea. You touch something to the top, that top plate, and charges build up, and so now the hollow straw becomes charged, and actually you can see how far it moves. You can actually read the amount of charge it's got. Okay, here's a gold leaf, almost identical to the one I showed you. This one is a flask, like same thing though, but it's built into a flask instead of that little box I had. And there's a pith ball one, which I showed you before. So let me look at that one again in detail. So we start out with the pith ball. It's neutrally charged. Okay, which means, remember, that's not a charge. Neutral just means it has the same numbers of positive and negative charges in it. You bring a charged rod, which is what I did, towards it. I didn't touch it. I was careful not to touch it at first. And what's happening, again, the positives rush towards the negative charged objects, and the negative go the opposite direction, because, you know, likes attract, opposites attract, likes repel. So the like ones go far away. Now, if I gave those negatives a way out, this would be induction, but we're not going to do that. So then I go ahead and touch it. Now it becomes one object. When it's touching, it technically becomes one object. And so the charges kind of spread out through that one object. Well, because the rod was much bigger than the pith ball, the negative charges can't neutralize the rod. What happens is, though, the rod becomes, this is what didn't happen with when I showed you this, but the rod becomes overwhelmingly negative still. And now the pith ball's a lot negative too, because it lost some of those positive charges. So now it'll repel it. Okay, and that's what I was trying to get it to do. And I did not succeed, so I have a video of that happening. Charging by friction. See, it's repelling it because the pith ball is neutral. You touch it, make it more neutral. Just to make sure it's neutral, you let it discharge. Okay, charging by friction. He's bringing it close. And it's attracted to it. And finally, when it lets it touch it, he's going to let it touch it. Now they become charging by conduction. Now they become oppositely charged. They become like charged, so they're repelling each other. So before it wanted to go near it, now it wants trying to stay away from it. And again, you can see that this is much stronger force than gravity because it's overcoming gravity. Okay, one more time. So it's attracted to it. It's attracted. Oh, and then once it touches it, it doesn't want to go near it. Because now they're like charged. All right, I think that's it. So we have conservation of charge. Okay, there's the four great conservation laws: conservation of mass, conservation of energy, conservation of momentum, which we talked about first semester, and conservation of charge. And hopefully you played a little bit of this in chemistry. And it's pretty much like the other ones. Charge can neither be created nor destroyed. It can simply be transferred. Now, I kind of hinted before with the close sticking to you that it can be problematic, right? This static charge, there's static problems. So there's some kind of annoyance there, but also there's some serious problems if you guys, and some of you do, play around inside computers. Even if you just open a computer up to add more memory, there's a possibility of static discharge, and particularly those memory chips and even the CPU, all the integrated circuits in there. There's a danger of destroying them. Not just oh, we'll reboot the computer. No, that's not going to work. You actually destroy them with static discharge. So if you let's say you rubbed your feet on the carpet or something, and then you went and opened up the computer and you had a discharge to one of those IC chips, you would destroy it. So what you have to do is you have to do like the bottom picture where you ground yourself to the case. The case should be grounded because it's plugged in to the electrical system of your house, and the electrical system, it has to have a ground by law. We actually had to drive a I think it was 30-foot, 15-foot copper rod into the ground in my house to ground the electrical system. And you drive it into the ground, and then you attach it. You attach the electrical system, the whole house, to it. And so every outlet is grounded. This is a famous disaster. This is the Hindenburg. This is in the mid to late 30s. I don't remember the exact date. The Hindenburg, the Germans were big into traveling airships, and they filled their airships with hydrogen. The other choice would be helium, but the United States had the world monopoly on helium. We were the only ones that had helium, and we wouldn't sell it to the Germans. We considered it a strategic material, and so we weren't going to sell it to anybody. And so the Hindenburg was making a run from Berlin to New York. It docked in New Jersey across the river from New York. And it picked up static charge on the way because it's running through the air and it's not grounded on the way across the Atlantic. And it's running through the air, so there's charging by friction, a lot of charging by friction. And when it got to its mooring station, that metal mooring station here on the right here, this thing on the right, it was going to attach here. As soon as it got close, a large spark went off. Remember, the thing is full of hydrogen. Hydrogen is highly flammable. It was leaking, so there was like a cloud of hydrogen hanging around. It caught fire, and terrible disaster happened. The other thing you have to be careful of is this. And you see these warnings at gas stations. This is static electricity can cause refueling fires. Always discharge static electricity on the door frame when you exit your vehicle. The shock you feel is your protection. So the idea is that a lot of car seats are made of artificial materials, and by rubbing across them, by getting in and out of the car and other things, you build up a static charge. So when you stop to get gas, the idea is you touch your door frame and the metal, you'll discharge to the metal of the car. And before you get near the gas fumes that are coming when you start refueling, gas fumes come out. Gas evaporates easily. And so gas fumes start coming out and gathering around the where you put gas in. That's why we have some places, particularly in Southern California, have those gas recycling, because it's considered a pollutant. So we want to suck that evaporated gas back up. You don't find that everywhere. You kind of like have been living in most of your lives, probably if you lived here in Southern California, you've had those on gas, or you haven't even pumped gas for your parents or for yourself, but that's what they're for. But if you don't have those, gas accumulates around there. It doesn't necessarily, if the air's still, it's not going to mix too quickly, and you can set it off, like in this video that I'm about to show you. Okay, so watch this woman get out of the car. Watch her not touch the door. Kind of, yeah, see that? She didn't touch the door. And she's got this sweater or hoodie she keeps playing with too. So there's a lot of rubbing going on here. And see now that nozzle might not be the nozzle you guys are familiar with. It has no vapor recovery system on it. It's just a nozzle, and she rubs her pants and she starts pumping. She gets back in the car, but she doesn't touch the door again. And look, her leg is up, which means she's probably reaching over to the other side. So she's probably rubbing on the seat. And she gets back out without touching the door again. and bango, she sparked as she got close to the metal there. She sparked it. By the way, you know, when you go to a gas station, you should make yourself aware of where the emergency shutoff is. They all have them. Somewhere in an obvious sight, there's an emergency shutoff. What it does is it'll shut off all the pumps. In case of something like this, where there's a fire, you want all the pumps to shut down. And so you hit it and it'll shut them all down. Let's try some questions. You guys just answer, not the same person every time though. When a glass rod is rubbed with silk and becomes positively charged, so the glass rod becomes positively charged, the silk remains neutral? A. B. Protons are added to the silk. C. Electrons are removed from the rod. D. Protons are removed from the silk. Think about it. Give me an answer.
Would it be C?
Yes. Okay, so remember, we're always talking about electrons moving. So the silk, if the glass rod becomes positively charged, so if the glass rod becomes positively charged and the silk becomes negatively charged, that means the silk gained electrons. So it got more electrons on the silk. And by the way, that doesn't mean that electrons are positive. It means that there's more of them. Okay, so the silk gained electrons. So where did the electrons come from? They came off the rod. The electrons are removed from the rod. Now, protons are added to the silk. Well, that would make the silk positive. The silk's not positive. Protons are removed from the silk. That would be a possibility. But again, protons aren't going to move easily, particularly if in this kind of dry situation. So the electrons are what's causing the movement of electrons, are what's happening. That made the rod positive. The glass rod became positive because it lost electrons. So they must have gone to the silk. Come on, you guys, this one's easy.
B.
Yeah, always conserved. And which sentence best characterize electric conductors?
D.
D, they have electric charges that move freely. By the way, they are great conductors of heat, so they're great conductors of heat. For the same reason as they're great conductors of electricity too, by the way. Process of a charging conductor by bringing it near, but not touching a charged object, and then grounding the conductor before moving the charged object away is called?
C.
C, electrostatic induction. Yes. Okay.